AdBlock Plus is the major product. I think it's popular with this product. And today we will talk about self-supervised learning, representative learning in computer vision. We will focus on contrastive learning, not on generative models. Maybe we will just review previous works on self-supervised learning, and then we'll focus on two works which are momentum contrast and simple framework for contrastive learning from Facebook and Google. I would recommend you to these two lectures from New York Center for Data Science and from Berkeley University about self-supervised learning. Okay, let's start. Self-supervised learning. Self-supervised learning is machine learning when labels are simply generated by the modification of the original data without human in the loop. There are many approaches, generative models like autoencoders when labels are the original images or maybe slightly modified images, discriminative learnings when labels are meta-information about original images and maybe part of images, position of images, etc. Labeling data is expensive. Labeling images for classification tend to be biased and has an errors. One of the biggest data set is ImageNet data set, classification data set, and mostly models are pre-trained on ImageNet. Mostly all new models or all well-known models and approved models, which they mostly all are pre-trained on ImageNet. So you can easily get pre-trained weights on ImageNet in fully supervised manner for classification. And labeling data for detection and segmentation is at least twice expensive and biased. We have experience with data labeling and we permanently correct our labels, use different labeling services, and etc. Pretext tasks and downstream tasks. Pretext tasks on which model is trained for better representation. It might be autoencoders, it might be context encoders, and one view from another, contrastive learning, which we'll discuss later in this presentation. Downstream tasks on which features learned from downstream task, from pretext task, sorry, excuse my mistake, is used as an input for other task, for downstream task, or fine-tuned entire model. For instance, classification, object localization, backbone for object detection or semantic segmentation, feature extractor for image retrieval, image captioning, etc. ImageNet vs custom data. ImageNet has over 1 million labeled images with fixed size range and 3 channels. Objects are mostly in the central area of the images. It has limited brightness, contours, etc. And maybe augmentation helps, and actually it helps a lot, but sometimes our custom data might be completely different. It might be grayscale images, X-ray images, old images, multi-channel images like MRI with 8 channels. Object location might be in different corners, satellite images, images from drones, images from microscope. For instance, in these microscope images, image center cropping, would be damage our performance instead of increase. Here is another example where, for instance, in classification, we need different areas of these images. Here is an example of satellite images. When we have detect or when we have classify, and we need information from different parts of images. Another example of satellite image. X-ray images. Classes of self-supervised learning. I think it's obvious, but as I mentioned above, labeling is expensive and time-consuming. Mistakes are almost inevitable. Labeled data for classification contains small amount of information in comparison with images which has other different objects. Multitask learning adds more difficulties and hyperparameters. Multi-object classifiers need more labeling, and multitask learning, we can use multitask learning or multi-object classifier to extract more information as pretext task from the extract more features from the images, more informative features from the images, not more features, excuse me. So ImageNet pre-trained models perform pretty well on even different domains, but we have an alternative. But if we have an alternative, pre-trained images for this similar domain, similar data, train images on custom domain, and put these pre-trained models in public, different model architectures. Maybe we have images and we need different architecture, and for instance, for classification, or use different architecture as a backbone for object detection, and our custom data set is completely different than ImageNet data set, and we have no alternatives. We should use ImageNet pre-trained models unless we don't have unlimited resources to train our model, label and train our model and use it as a backbone. If we have good enough self-supervised learning methods, I think many companies or volunteers or students or academia will provide with pre-trained models on the different domains, and we can find similar domains to our data set and even similar models which we are looking for pre-trained on the similar domain. Probability is higher. It's obvious. This is the Jan LeCun's cake. They call it LeCun's cake. When he classifies different approaches of learning, and pure reinforcement learning is a cherry of this cake. Machine predicts color reward given in while a few bits of some samples. Supervised learning icing, when we have from 10 to 10,000 bits per sample, and self-supervised learning, it's entire cake inside of cake. I don't know this word, gnosis or gnosis. The machine predicts any part of its input for any observed part. Predicts future frames in videos, millions of bits per sample. Excuse me, I think I need to adjust. Good. First thing which comes in our mind for self-supervised learning is, of course, autoencoders. Autoencoders learn from the original images they encode and reconstruct the data, we can separate after the training, take only encoder and use it as a feature extractor. This approach, it works in some cases, but it doesn't have significant performance gain to compare with fully supervised trained data. Denoising autoencoders is another alternative when we damage the original image and try to reconstruct it and then use encoder as a feature extractor. Context encoders from this paper. When we reconstruct the part of the image, when we extract part of the image, it's just kind of similar of autoencoders, but model will learn and predict. Model has to reconstruct, for instance, central part of this image, and it has to learn entire image to reconstruct it properly. Context encoders enriched with adversarial discriminator for training. Here are the examples of reconstruction with simple L2 loss, Euclidean loss, with adversarial loss, and with joint loss. They performed, here are the, and back there people, researchers mostly used AlexNet, as well as I know. Here are the comparison of the models, self-supervised models, trained with different approaches. The last one is context encoder, training time, classification accuracy, and as you see, gap is quite big, even for detection and segmentation. The other approach was colorization. I think you also on Twitter or on Facebook, it's brilliant, de-oldify news and messages when they colorized old images, even they colorized first movie. And colorization, turns out, works quite good for downstream task, but doesn't perform as well on pretext tasks. Gap is still big between fully supervised learning and self-supervised learning. Relative positional image patches was another approach when different, when from central patch, model has to classify from 8 possible positions of the other patch from these 8 positions. And model did extract information from positions, and model also extract relative information. It was one step towards reducing the gap between fully supervised and self-supervised learning. The other approach was solving jigsaw puzzles. Excuse me, I think I have to mute my phone. When 9 different patches are extracted from images, mostly from central part of images, they are shuffled, and model has to reconstruct the order of the patches. Of course, they use simple classification approach. Of course, the magnitude of possibilities of patches is high, so they use only 100 shuffles and 100 classes in classification, different classes in classification. It also gave performance gain, and I think, as well as I remember, it was the first model which on the with AlexNet backbone, not with ResNet, outperformed fully supervised backbones on object detection on Pascal-Vogt dataset, I think, one of the benchmark datasets. Rotation classifier, it's simple and straightforward approach. Images are rotated in 4 different angles: 90 degree, 270 degree, 180 degrees, 0 degree, and 200. Yeah, sorry, I'm just reading. And model has to classify, model has to detect rotation angle. It was quite simple approach, but images are different. For instance, here in first image, this might be natural position, even on second image. Dog just can't be on the slope, and model has to also pay attention on background to predict correct rotation angle. Here, for instance, frog. It might be on wall, on horizontal or vertical position. And here, I don't see, is it furniture or something? Yes. So model need to extract more information, background information from the image. And sometimes not only background information. For instance, here are 2 human faces, and the model has to pay attention of different part of faces, on nose, on eyes, lips, chin, head, and also learn position of the different part, proper position of different part of face, for instance. So this simple approach give better performance gain. Here are the comparison. They tried different approaches. They increase angles of rotation, but model performance dropped a little bit. They decrease rotation angles. Still, model performance was less than original 4 angles. So I don't know why, but this 4 angles was the best approach, and as well as I remember from the paper, performance, they increased performance by putting all the possible rotation of the same image in one batch. I think batch normalization, it was batch normalization, or if they use AlexNet, I don't know. Here are the rotation classifier, pre-trained model on rotation classifier, and extracted features not at the end, at the top layers, from the top layers, but features from the middle layers, or before top layers, in Con4 and Con5 layers of AlexNet, and then trained on downstream tasks. And as we see, rotation classifier gives pretty much the similar performance as ImageNet trained from scratch on the first layers. And then performance is lower on the last layers. Here are the other examples. As you see, on after the first convolutional layer, it has almost the similar performances fully supervised trained network. Here are the comparison of classification. I don't know. I think it's Pascal Walk and AlexNet. And I think it's classification Pascal Walk VOC dataset or Walk dataset, and classification, detection, and segmentation with mean average precision and mean intersection over union. And as you see, rotation classified pre-trained backbone is rotation classifier. Pretext task performs almost similar as fully supervised models trained and trained on with fully supervised manner. Instance discrimination. The major performance gain gave instance discrimination approach. When the same image was augmented with different augmentation, and model has to attract representation of the same with different augmentation of the same image and repeal the representation vector from the other randomly selected image from the dataset. And we will focus on two major works in this direction. One of them is momentum contrast, and second is sim CLR or sim CLR. Softmax on peers. Just recall softmax loss when we normalize exponentials of our vectors and get the probabilities. And then we can use cross entropy to train our model. The same approach we can use for peers. Take anchor and positive peers. In our case, it will be images, the same image with two different augmentations, and compare with the anchor and all other images. And let this f function will be distance function. Maybe angular distance or just vector product, scalar product of the representation vectors. And if the scalar product is bigger, then the appropriate vectors are closer to each other. So to make this scalar product higher, we need to make this part higher and bigger. And the proper way to make this part bigger is to use softmax on these peers. Bigger than all other peers. You can recall word-to-vec with skipgrams. I guess approach is similar. But all negative pairs from ImageNet means more than 1 million negative pairs. And per each iteration, we have to call our model more than 1 million times. It's almost impossible. So we can take big enough amount of negative samples, randomly selected samples, and call it negative pairs. So instead of compare with all negative pairs, you just take big enough negative samples and do the same with softmax. But even big enough samples, turns out, is hard to train. First of all, we have to run fast forward on anchor, on positive, and big enough negative pairs. Then we have to calculate loss. Okay, it's not a big deal. And then we have to backpropagate. One way is to save pre-computed negative samples. Run once our model or big enough negative samples, save vectors, use them as a negative samples. But after weight changes after backpropagation, negative vectors should be different. We have to somehow make them as close as possible with features extracted by the current model with updated weights. So first thing which comes in mind is moving average. I guess moving average is the solution. So let's look into the momentum contrast approach, which was introduced. I think this name is familiar for you, at least if you did work with RCNN models, especially faster RCNN, I believe. He's one of the authors. And in this paper, they save negative pairs in Q. Why Q? Because Q has the property that it will remove fixed size Q, of course. It will always keep hot negative pairs, I would say. Closest negative pairs with the original encoder. And let's look. They extract these negative pairs from Q and they use the softmax approach. They also use temperature parameter, which is hyperparameters and increase performance. But it's not a major component, I would say, in this approach. It was introduced before them, but the initial model initialized the model. Let's dive deeper. How do they refill this Q? They initialize model and make a copy. Let's call first model query model FQ and make a copy and call it FK, K model. And they also have introduced fixed size Q. Then they take image with two augmentation functions, AQ and AK. Of course, these augmentation functions are not fixed and only two augmentation functions. They are dynamically, for each iteration, selected from the fixed class of augmentations. Maybe once AQ might be center crop and AK might be grayscaling, or AQ may be grayscaling on second iteration, and AK will be noising, adding the noise to the original image. So they augment the images, the source images, call it XQ and XK, calculate representation vectors with FQ and FK, calculate the loss, propagate only FQ, so the weights WQ, Q are updated, and then update weights of FK with the exponentially moving average. from FQ and save representation K in the queue. So they remove the oldest, thus least influenced feature by FQ, and they put their hot feature vector, closest feature vector generated, not closest, but closest in term of Euclidean or metric, but closest to the feature vectors generated by the model with current weights, I would say. If you have a question, you don't understand, and something is unclear, you can ask me or write me. I just won't get notifications because during the presentation, I put my laptop on do not disturb mode. So
I will let you know if there is a question, Levon. Don't worry.
Okay, thank you, Hunt. And just remind me time if I'm out. I need to let 10 minutes, I believe. So in Q are the representation vectors generated by the FK, not by the FQ. Lower the index is Li is updated with FK with closer weights with FQ, which was updated by the backpropagation. I'm just repeating myself to make it more clear. The less influenced vector from the last update, not last but previous update, sorry, it was my mistake, then they are removed automatically from the queue. So they have less influence on the negative samples. This is the manner algorithm maintains the better, the hotter representation vector for negative samples. This is just my opinion, but this works plus because the K vector here, this K vector also, in positive sampling, is also calculated with FK model, not with FQ model. Somehow they are in the similar domain, I would say. And this K vector is calculated before FK's weights are updated by the momentum of FQ's weights, by the moment of shifted moment of FQ's weights. So this weight was updated in previous iteration is exponentially moving closer average of FQ model, closest to the backpropagation weights. Now, just translate everything in batches. Instead of one single image, just translate and consider each call as a batch. So if our queue has length n and our batch size is k, or just we already use k, our batch size is b, so we have already LB. We can L times B in our batch size. We can consider that we have L times B batch size. Not L times B negative samples, because in batch we have different samples, but L times B batch size. And bigger batch size obviously means better performance, bigger negative samples. Yes. So here is the original pseudocode close to PyTorch style or PyTorch-like style from the original paper. And I guess it's quite simple. That's why I'm involved with this paper. It's simple ideas, several simple ideas together, and they work. Here, the initialize models, just for initialization, call augmentation, call forward, call for Q with FQ and for K with FK. They detach K to avoid backpropagation gradient calculation on the K. Just with batch matrix multiplication, they calculate positives. With matrix multiplication from Q and K, they calculate negative pairs, calculate logits. Labels are zeros, of course, and they use cross entropy loss. Just binary classification for each pair. And they use 0 as a positive class. Then update with backpropagation, and recall K was detached, only FQ's weights are updated. And then they update FK's weights with exponentially moving average from FQ's weight. Averaging, exponentially moving, averaging FQ's weight. Then NQ, the K, not Q, they NQ the K, and DQ the last preserved vector. Here are three different approaches. First is end-to-end training for positive and negative samples, which needs huge batch sizes, huge amount of data per batch, I would say. This is approach of memory bank, which I mentioned, but I did not put the paper. There actually was a paper. They use memory bank, and they just randomly extract images, vectors from memory bank, and randomly put other vectors. It worked. It gave performance. It was one step forward. But here is the momentum contrast, which works, and it's obvious, works better than previous two approaches. For end-to-end training, here in this image, we can see that after 1,024 batches, we don't have capacity unless we are not Google and or Facebook and have unlimited resources of GPUs. And we will see how Google outperformed momentum contrast. And here is the memory bank approach. And as we see, the batch size, not batch size, the sample size, actually the negative sample size increase the model performance. And in momentum contrast, you see the gap between memory bank and momentum contrast. Memory bank was just pre-saved vectors, representation vectors, and randomly updated some of them, I would say.
Levon, so x-axis in that previous image is the number of negative samples in the softmax?
Yes, yes.
Yeah, that is huge.
Yes.
Okay.
Its number of images per maybe it's not a number of negative samples. It's batch size, actually. How big batch would be plus memory, plus Q or memory bank.
Okay.
They also train different architectures of ResNet, ResNet 50. ResNext 15, wide ResNet, when they use wider convolutional feature maps, 2 times wider and 4 times wider ResNet. And you see performance, how performance is improved, but parameters also are bigger. And they almost achieve, not almost, but they achieve significantly improved performance in comparison with end-to-end classification, pre-trained, fully supervised pre-trained models. But Google came with different approach, with simpler model. Actually, it was Google Brain's paper. Geoffrey Hinton also was involved in this paper. They use fixed augmentation technique, and they use end-to-end here with huge batch size, and instead of use direct representation vectors of the original model H, they use smaller two-layer projection on top of the original model. Excuse me, do you hear me? I think.
Yes, you're back.
Yeah, and when I should I repeat? And when I was...
No, it's okay. It was a couple of seconds, so you have still 5-10 minutes, so please.
Okay, so they use two-layer projection model, and they proved that with this projection layer, after we remove this projection and use original models representation vectors produced by the original model, it improves performance, and it improves performance significantly. This is the algorithm of the simple trade. It's quite simple and original also, but still it needs, they train on TPUs, and they have huge amount of TPUs, and they use big batch size, and they also proved that bigger, wider model perform better. They also show that in comparison with supervised training, more epochs, more iteration gives performance improvements, while on the supervised, with the supervised model, after 100 epochs, performance didn't change. Performance won't change much, but in self-supervised learning, more epochs means more better performance, and as you see, even wider models, 4 times wider models, in comparison with fully supervised training, wider models also give performance gain, while there is no big difference between 2 times and 4 times wider models for fully supervised training. I think this is because this approach needs more information to save, to extract more information, and that's why wider model in bigger dimensions, they can extract more information from the single image in comparison with supervised models. So after that, they took Facebook researchers, they took they also took the same approach, the same they went the same way, and put the projection head to the momentum contrast training. So they call it improved baselines with momentum contrast, momentum contrastive learning, and they use momentum contrast approach, but they put projection header, and they refine augmentation. They also slightly change augmentation produced in SimClar, and after all, even with less epochs, they achieve better accuracy. And you see that they, on the walk dataset, which has small amount of data for object detection, they achieve more average, better average precision than supervised models, and they achieve, I would say, significantly better average precision than fully supervised model. Here is the comparison of Mocha version 2 with SimClar model. Even with less iteration, their model performs, their trained model performs better. On ImageNet, retrained on ImageNet, and with transfer learning on ImageNet, they only train last classifier layer. And as you see, it performs better with less epochs and less calculation. I did not put it here in presentation, but when I publish this presentation, I will put. There also are different approaches. Worth to mention, it was simpler. Two, it was two papers which I did not understood. One was, I think, from Google, from DeepMind, I think, know your own latent, when they did not use negative samples and use the similar approach, but I don't understand how they gain significant performance improvement for ImageNet classification. And second was contrastive clustering from Facebook, when they cluster and use the same contrastive approach at the same time online without pre-clustering and then training. And they also improved accuracy, classification accuracy on ImageNet, but they did not improve detection accuracy, average precision on work dataset. That's why I did not put it there, and I need to understand them better to put it there. But anyway, using pre-trained backbone, ResNet 15, we trained faster RCNN with ResNext 101 backbone pre-trained on ImageNet in fully supervised manner, and Moco version 2 pre-trained ResNet 15, also for faster RCNN on our task for on the 50K screenshots and 10K screenshots in IO to detect ads. So faster RCNN with ResNext 101, bigger backbone, more layers for feature pyramid network for RCNN, higher dimensional features, wider model, 32 parallel convolutional blocks in each residual block, and deeper model, 101. Faster RCNN with ResNet 50, smaller model, less layers for feature pyramids, only one layer instead of 4, lower dimensional features, narrower model, one convolutional block in each residual connection. Shallower model, only 50 layers. Performs less accurate on true positive, performs better on false negative with 0.5 confidence threshold, higher recall, lower precision, well, 0.98 confidence threshold, classification confidence threshold, lower recall, higher precision. Better fits for our demands. Here I put the, as you see, this is model trained on, this is my mistake. Here should be 50K dataset, 50K hand labeled and plus synthetically generated screenshots with ads. Here are true positives. Here are true positives, false negatives, false positives, recall, precision, confidence threshold, intersection over union threshold, and mean average precision. And as you see, excuse me, the second one should be ResNext 101. Oops. Sorry. Oops, my bad. Sorry for that. Just give you our examples. Here you see difference in performance for 50K data set. Here is the Moco and ResNext 101 different backbones, trained on different manner, full supervised and self-supervised manner. And our main problem is false positives. It's better to hide to hide less ads than hide actual parts of web pages. So you see that and this part should be 150K dataset, my bad. And you see that on bigger data, on smaller confidence threshold, ResNet 101, ImageNet pre-trained outperforms MoCo, but on bigger confidence threshold, it outperforms fully pre-trained model, even bigger model, which naturally should be way more better than last one, ResNext 101, with more feature pyramids than ResNet 15. Here I put first one is ResNext and second one is ResNet, and we have significant drop in false positives. And the model outperforms human level annotators, but in human level, unfortunately, ResNext worked way more better on 50K. And this is different benchmark, 200 benchmarks. We choose non-professional annotators, non-professional ad blocker annotators, and gave them task to detect ads on 200 screenshots, one of our benchmarks. But unfortunately, ResNext outperformed our momentum contrast trained model. But still, it was 50K dataset, one bigger dataset, and more iteration. We observed performance gain, and we still are working on these backbones. So for future, we are hoping to use momentum constant version 2 pre-trained weights for that model, which is transformer-based object detection model. I think this answers one of your questions, Grant, about transformer in images. We trained this model with ResNet, pre-trained ResNet 15 and ResNet 101 backbones, but they did this model. They didn't give us sufficient performance in comparison with faster RCNN models, original models. Maybe MoCo pre-trained backbone will give us performance gain. Fine-tune MoCo on our custom datasets. We have different datasets, especially in Maxin.ai. Take pre-trained MoCo model and fine-tune, but with the same method, the same MoCo method, not fine-tune on the particular task, but fine-tune the same MoCo method with initialized MoCo pre-trained weights, less computational resources, less data. Use different models, which unfortunately are not provided by the Facebook. Train different models with self-supervised learning on custom dataset, maybe ResNet 34 for smaller dataset, wider ResNet for maybe fine-tune for bigger datasets. Find proper hyperparameters for different domains, different augmentation for different datasets. As you saw, ImageNet has different distribution of objects, and our datasets are quite different. Different learning rate policy, fine-tune with discriminative learning rate, progressive growing approach, train on small images, then on bigger images, and then on bigger images. One cycle learning may be different moment for our different temperature parameters. But this is our future plans. If you have any questions, I think I'm ready to answer.
Thanks a lot, Levon. Unfortunately, you did not hear the applauses for your talk. So we have one question and 3 minutes. So the question is from Sipan Muradian. He said, maybe he missed this part, but if we don't have labels for the images, how do we make sure no positive examples are sampled when choosing the negative ones?
Yes, this is the good question.
Yeah, you see the question, right?
Yes.
The confusion is that how do we actually choose the positive ones and what is considered as positive?
As positive considers the same source with different augmentations. The same image with different augmentations are considered as positives. But they might be from the same class. For instance, we might have dog here, but it won't be the same dog because we only choose once, one image. Make two augmentations, for instance, grayscaling and cropping, and consider them as a positive pair. After all, it is because of data distribution in ImageNet, at least. We know that we have more than 1 million images and only 1,000 class. Yes, we have 0.0001 probability that we will take from this similar class. And the second is, it won't be the same image. It might be the same class, same dog, but it can be considered as a different image. We are not classifying here. Our downstream task is not for classification. Our downstream task is just for feature extraction. And augmentation of the similar images extracts features from different than on pretext task. It is robust against image changes, not entire shifting of domain, but against different views on this of this same image. It extracts similar features from the similar images, I would say. But after all, our task is not to classify. It's not classification. Our task is just feature extraction, good representation. But yes, we have probability that we will have dog here, the same class here, but not same images. Does it answer your question?
I think so. We'll see if he writes in the chat. So thank you for the answer. I have a couple of more questions, but I think I will leave this for Slack. So my questions are about on what you have pre-trained and why do you not use larger datasets than ImageNet. But let's leave this for Slack discussion. Let's move to our next speaker. Thank you very much, Levon, for this talk. And we hope to also see you in the panel today.
Thank you very much. I just forgot to put last slide. Thank you. Thank you very much. It was a pleasure.
Perfect.